The flywheel and the clutch cover on the engine side are united by bolts. Inside the clutch cover, there is a pressure plate which pushes the clutch disc against the flywheel, usually by a diaphragm spring. This pushing power transmits the rotational movements of the engine to the transmission through the input shaft splined with the clutch disc. This is a condition called the clutch is engaged. When the power pushing the pressure plate against the clutch disc is lost, the clutch disc becomes free between the flywheel and the pressure plate. This is a condition called the clutch is disengaged. The clutch that is now being pushed is the type which disengages when a pushing force is applied to the small end of the diaphragm spring. There is another type to release the pressure plate using a pulling force by reversing the fulcrum and the action point of the diaphragm spring. Compared with the pushing type, the pulling type allows a bigger release lever ratio A to B. Accordingly, the bigger pushing force against the clutch disc does not make the operation of the clutch pedal heavier. Here is how the clutch functions. Depression of the clutch generates the sliding movement of the piston. In the clutch master cylinder, that sliding movement converts to hydraulic pressure. The inlet valve closes the reservoir passage. The elevated hydraulic pressure is transmitted to the release cylinder. Using the hydraulic pressure, the release cylinder piston pushes the clutch release fork through the push rod. And then the release bearing installed on the other end pushes the diaphragm spring in motion. In this way, the clutch disc can be released from the pushing of the pressure plate by the diaphragm spring, and the clutch is disengaged. Here are general explanations of 4 problems found in on-vehicle inspection: clutch disengaging problem, clutch slips, clutch engaging problem, and unusual sounds or noise. First, put stoppers under the wheels. Fully apply the parking brake. Depress the clutch pedal and start the engine. Confirm that the shift lever is in the neutral position and release the clutch pedal. Then shift the lever to the reverse position and wait for the gears to make a slight crunching sound. Since the reverse gear does not have a synchronizing mechanism in most transmissions, the gears cannot be engaged easily or sometimes cannot be engaged at all when the clutch has a disengaging problem. So the problem can be identified more easily than by shifting into a forward gear. While the gears are making a continuous crunching sound, depress the clutch pedal slowly. Never try to shift by force at this time. As the clutch pedal is further depressed, if the continuous crunching sound stops and the gears shift smoothly, the clutch has no disengaging problem. Clutch slips means that the clutch disc slips between the pressure plate and the flywheel when the clutch is engaged. If the clutch slips, the engine power cannot be conveyed sufficiently to the transmission. Here is the inspection procedure. Follow the same procedure as before until the engine starts. Shift the lever to the low gear. With With the engine idling, release the clutch pedal slowly. The clutch is not slipping if the engine stops at this time. Never test for a prolonged time, as this test could overheat the clutch. This is where the driver feels intermittent vibrations and is shaken back and forth when the clutch is engaged. Or the vehicle suddenly moves forward when the clutch is partially engaged. In both cases, it may be concluded that there is a clutch engaging problem. Such conditions may not be noticeable in ordinary driving, but will become more noticeable when the car is started on an uphill grade or with a heavy load. Unusual sounds or noises may be heard from the clutch when it is depressed or released. Put stoppers under the wheels, depress the clutch pedal and start the engine. Put the shift lever in the neutral position and release the clutch pedal. Depress the clutch pedal again. And repeat, both slowly and quickly, to check the presence of unusual sounds from the clutch. If unusual sounds or noises are heard, check to see if they come from either the clutch or the transmission side. If trouble is found in the course of the on-vehicle inspection, it is necessary to remove the clutch cover and the clutch disc for further inspection or treatment. Here are the basic procedures to follow in removal and installation. Put match marks on the clutch cover and the flywheel. And then set the crankshaft pulley holding tool. Loosen the set bolts in several passes in diagonal order. Remove the clutch cover carefully so as not to drop the clutch disc. Wipe off any abrasive particles on the cover carefully. Remember, keep the clutch disc facing, the pressure plate and the flywheel free of oil or other foreign matter. After necessary treatments, install the clutch disc and the cover. Apply a coat of molybdenum disulfide lithium base grease on the clutch disc splines. Be sure to set the clutch disc with its protruded side facing the clutch cover side. Insert the SST in the clutch disc. And then set the cover in position. Set the clutch cover according to the match marks. Gradually tighten the clutch cover set bolts in diagonal order, starting with the one near the knock pin. Before completely tightening the bolts, move the SST in all directions to make certain that the clutch disc is right at the center. Tighten the bolts to the specified torque. The transmission is an assembly of gears that converts the engine rotation, torque, and the rotational direction depending on the driving conditions, and transmits them to the drive wheels. This is a demonstration using simple models. Two motors with the same power representing the automobile engine pull the weights. The shafts of the two models used to wind up the threads holding the weights differ. This difference corresponds to that of the number of gear teeth of the transmission. The one with less teeth does not show any significant work. On the other hand, the one with more teeth lifts up the weight slowly due to the bigger torque it can generate. This is the same as the combination of gears automobiles use for starting or driving uphill. Now, relatively light weights are used. Both models are doing their work, but the one with less teeth can lift up the weight faster. Such combination differences allow automobiles the speed range from low to high. The transmission is an assembly to operate a combination of different gears easily, promptly, accurately, and quietly. How many gear changes would be practically ideal for a transmission? The ideal driving performance curves show continuous engine torque changes. With two shifting gears, as in the previous models, the inefficient use of engine torque, the portion shown in red, increases. On the contrary, too many gears will complicate the construction and operation of the transaxle transmission. Accordingly, it is common that the number of gear changes should be 4 or 5 in forward speed. With a combination as shown in the previous models, the rotational direction of the force input side is opposite to that of the output side. Therefore, in practice, two combinations of gears are assembled to obtain the same rotational direction. Since driving the wheels in reverse to back up a car is one of the functions of the transaxle transmission, one play gear is added to compensate for the engine that cannot reverse. Manual transaxle transmissions may be mounted either transversely from side to side or longitudinally from front to back. FF vehicles usually have transversely mounted transaxles, while FR vehicles have longitudinally mounted transmissions. The following is an explanation of the simple construction and function of the powertrain of W58 4FR vehicles. To observe the gears better, the input shaft side is on the right of the screen. From the first to the fifth gear, except the fourth, power is transmitted along the input shaft, main drive gear, counter gear, respective gears, clutch hub sleeve, and output shaft. In the fourth gear, the input shaft and output shaft are directly connected. In the reverse gear, the idler gear is added. This gear makes the rotational direction of the input shaft opposite to that of the output shaft. The C50 transaxle for FF vehicles has different characteristics compared with the W58 we have just seen. Its differential is incorporated to make it smaller. The input shaft and output shaft face the same direction. Shift changes can be made by a wire in the remote control system. In the powertrain, there is no equivalent of the counter gear in W58. Now, here is a brief look at the powertrain of C50. In the first and second gears, power is transmitted from the input shaft, respective gears, clutch hub and sleeve, output shaft, and then to the differential. In the third, fourth, and fifth gears, power goes from the input shaft, clutch hub and sleeve, respective gears, respective drive gears, output shaft, and to the differential. In the reverse gear, power is transmitted from the input shaft, reverse idler gear, reverse gear, output shaft, and to the differential. During gear shifting, two gears which rotate at different speed need to be meshed smoothly. One is the speed gear rotated by the input shaft, and the other is the hub sleeve rotating with the output shaft. Synchro mesh mechanism was designed to bring the two working gears closer to each other, using friction to synchronize their circumferential rotational speeds to achieve easy meshing. Here is an explanation of the functions of the key-type synchromesh, widely used in Toyota vehicles. The component parts of the synchromesh mechanism are the hub sleeve, clutch hub, key spring, and synchronizer ring. Before gear shifting, each speed gear turns freely on the output shaft. On the other hand, the clutch hub and the hub sleeve are respectively fixed to the output shaft by splines and rotate from the propeller shaft side. By moving the shift lever, the hub sleeve and shifting key move right, and the shifting key pushes the synchronizer ring, which has been free, against the gear cone to start synchronizing. Due to the difference in the rotational speeds between the hub sleeve and the gear, as well as the friction between the synchronizer ring and the gear cone, the splines in the hub sleeve and synchronizer ring face each other with a gap in the direction of the gear rotation. The size of this gap is equal to the difference between the width of the key slot and that of the key. Move the shift lever further. The hub sleeve rides up onto the projection of the key, and its spline tip pushes the synchronizer ring against the gear cone even more strongly. The friction generated by this action enables strong synchronization. Now the rotation speeds of the hub sleeve and the synchronizer ring are equal. The splines of the hub sleeve, which could not mesh with the synchronizer spline because of the gap, can now move smoothly and mesh with the gear splines and transmit the engine power. The speed gears and the spline inside of the hub sleeve have tapered teeth to prevent the transmission from jumping out of gear. This part of C50 shows the shift and select lever shaft, which incorporates the double meshing prevention mechanism, the reverse one-way mechanism, and the reverse miss-shift prevention mechanism. The reverse one-way mechanism controls the reverse idler gear to move only when the transmission is shifted into reverse. The reverse miss-shift prevention mechanism prevents accidental shifting directly into the reverse gear from fifth gear while the vehicle is in motion. The double meshing prevention mechanism prevents possible shifting into two gears at the same time. Here is an explanation of the double meshing prevention mechanism of W58, whose inside construction we usually cannot see. The central shaft has 2 slots, and each of the 2 other shafts has 1 slot. An interlock pin is inserted between the 2 slots facing each other. With the neutral gear position, there is a gap between the central slot and the interlock pins. When the central shaft moves up, the 2 interlock pins are pushed out and inserted into the slots on both sides to lock. Similarly, when the shaft on either side moves up, the pushed interlock pins lock the other 2 shafts in position. This is how the double meshing prevention mechanism works in W58. Each gear and bearing of the transmission is always subject to friction, so most of the trouble associated with the transmission occurs when wear or fatigue of parts exceeds certain limits over a long period of time. No matter what the problem is, identify the trouble using the driving test, and then proceed with disassembly and inspection, checking the parts suspected to be the cause of the trouble. In case of gear crunching while shifting into a particular gear, or more seriously in the case that gear shifting itself is impossible, suspect poor synchromesh operations first. Here are brief procedures of disassembly and how to inspect. Set the lever in the neutral position. Remove the shift and select lever shaft assembly. To prevent the shaft from turning, engage 2 gears. Break and remove the lock nut caulking. Disengage the 2 gears previously engaged. Using 2 screwdrivers of the same length, tap out the snap ring of the 5th gear in this way. Set the hooks of the SST to the gear correctly and remove the 5th gear, the clutch hub, and the synchronizer ring. Before disassembly, do not forget to measure and record the thrust clearance of each gear. Use a dial indicator for the 5th gear. As for the other gears, use a thickness gauge to measure the thrust clearance. In each measurement, check the thrust clearance around the entire gear circumference. This is the synchronizer ring. First, check the damage and wear of the synchronizer ring splines, which touch the hub sleeve. Then, push the synchronizer ring against the gear cone and rotate it to check if it slips or not. With the synchronizer ring pushed against the gear, measure the clearance between them with a thickness gauge. If there is any abnormality in these inspections, change the synchronizer ring with a new one. Beware of the projection in the middle of the shifting key that pushes the synchronizer ring against the gear, and wear and damage of the shifting key spring can also cause gear crunching during shifting. Measure the thrust clearance between the shift fork and the hub sleeve. Please remember, however, that problems of gear crunching or gear shifting difficulty at the time of shifting have a close